This video is to introduce you to the concept of sound waves. In this video, you're going to learn how sound is created, how your hearing works, how to diagram sound waves, and how to describe the Doppler effect. So, how are sound waves produced? We're going to look at this through the lens of a tuning fork, and we use tuning forks in physics to describe sound waves because it's really evident to see how the prongs on that tuning fork actually vibrate. Let's take a look at what I mean by that. So here is a tuning fork in slow motion. You'll see that each prong on the tuning fork actually exhibits simple harmonic motion because each prong is oscillating up and down, kind of like its own mass spring system. So what is that doing in order to make sound? What you'll see here is an animation of a tuning fork, and you'll notice as the prongs actually vibrate back and forth, they create areas of compression of the air particles and areas of where the particles are actually stretched away from each other. Where we have an area of compression, it's called compression, and where we have an area where the air molecules end up being less dense for a moment, that's called an area of rarefaction. So sound is produced when the air particles around the object that is doing the oscillating compress and rarefact those air particles in longitudinal waves. So here's the definition of rarefaction and compression. Compression is a region where the air molecules have a higher density. Every time you have an area where the air particles are at a lower density, that's called rarefaction. And how this is actually related to a sine wave graph, we'll see on the next slide. Here is a sound wave coming from a speaker. Every time you have an area of compression, you've got a crest on a sine graph. Every time you have an area of rarefaction, you've got a trough on a sine graph. And we can plot this with pressure on the y-axis, that would be the air pressure, versus time on the x-axis, and you get a beautiful simplistic sine wave. So now we know how a wave is created from a sound source, but now we need to know how we interpret that. So what I'd like you to do is pause the video at this point and take a look at the video labeled hearing, and that's going to give you a good 3-minute introduction to how our hearing works in terms of our eardrums. So humans can hear sounds that have a frequency between 20 to 20,000 hertz. It's a pretty big range, and that really is dependent upon the person that you're talking about. For instance, I don't think I hear that well anymore, and newborn babies may hear a little bit better because their eardrums are brand new and they haven't been worn out with age. However, if we have a longitudinal wave created from a sound source that has a frequency of less than 20 hertz, we say that sound wave is infrasonic, meaning we can't interpret that sound from our eardrums. If we have a sound which has a frequency of greater than 20,000 hertz, it's said to be ultrasonic. Dogs can hear ultrasonic sounds. That's why you have dog whistles that are used in training, because the dogs can hear the whistles, whereas humans cannot. So next definition of pitch. Pitch is a measure of how high or how low a sound is perceived to be. So you can have a longitudinal wave created from a source, but how you interpret that wave is the wave's pitch. Different longitudinal waves have different frequencies, and you interpret that frequency as the pitch of the sound created by that sound source. The other thing to remember is either a longitudinal wave or a transverse wave, they all have a constant velocity through a particular medium. The speed of sound in typical air is 343 meters per second. Take a moment and look on page 410 in your textbook. You're going to see a list of a whole bunch of different speeds of sounds through different mediums. Look at these values and then try to justify why some of the speeds of sound are faster than others, thinking about the texture of the medium that that sound wave is going through. So we like to think of longitudinal waves as one big straight line with areas of compression and rarefaction, but we also need to remember that sound waves actually travel three-dimensionally. So if my bell here is my sound source, remember that the sound waves will actually travel in a sphere away from the bell. That's what this diagram depicts. And that's why you have areas of compression and rarefaction moving away from the bell. And here is a good way to diagram sound. So I've got two things here. I've got a sound source, which is in the center, and I've got a sound receptor, which for all intents and purposes, imagine that's your eardrum. So the source will give out a longitudinal wave with areas of compression and rarefaction. I like to insert a ray from the sound source pointing towards the receptor of the sound. That's what this red ray is for. Every time I have an area of compression, that coincides with one of the crests on a sine wave, which is what this picture is trying to represent. And then also note that I have one final ring on the outside, which is the first initial compression from the sound source. And we call that first initial ring, that first initial compression, the wave front. And that is the first area of compression that will reach the receptor first. So as sound waves get further and further away from their source, those waves actually begin to look less spherical and more linear. And those particular types of wave fronts end up turning into what we call plane waves, because on the very outside of the circle, they almost start to look straight. And that's why the quality of sound, the further away you are, will actually change, because the actual plane of the wave will change as well. So the last thing to talk about here is the Doppler effect. And we use the Doppler effect to describe objects that are in motion that are also making sound waves. There are two videos I'd like you to watch. The first video is just for fun. It is one of my favorite clips from Big Bang Theory, when Sheldon Cooper dressed up as the Doppler effect for Halloween. And then the second video, again, has Sheldon Cooper in it, but also has a great explanation of the Doppler effect. You can find both of those videos on Schoology. You are now ready to do the assignment that is attached to this, which is on Schoology. If you have any questions, please let me know. Have a lovely evening.